Hello, once again, this is the Pencrest High School AP Physics 1 video series. This is video 8E, Sound and Hearing. Now, sound is a longitudinal pressure wave that moves through matter by direct transference of kinetic energy from atom to atom or molecule to molecule. The source of sound is a vibrating object. In the diagram below, the vibrating object is the cone or diaphragm of a speaker. The cone vibrates and the air next to the cone is compressed and stretched. These regions are comparable to the crest and trough of a transverse wave. Now we can see the air molecules here in between the speaker and this ear are alternately compressed and rarefacted. So this is analogy is the wave crest on the transverse wave that you see below. Now we're familiar with some wave quantities: period, frequency, wavelength, amplitude. Some of these quantities have specific applications for sound waves. Wavelength and period have the same usage and use the same terms. The frequency of a sound wave is what we associate with the pitch. Musical people will sometimes be described as having a perfect pitch, which usually means they can name a musical note based on a frequency, or they can reproduce that note perfectly with their vocal cords. Easily enough, high pitch is associated with high frequency, low pitch with low frequency. So fundamentally, the frequency of a sound wave is the pitch. Just for the benefit of the musical people, these are the frequencies that are associated with the chromatic scale. The series of octaves you see across the top here. Here is the middle octave, and here's middle C, 261.63. That's in hertz. All of these are in waves per second. And you can see as you go from one octave to the next, a given note is effectively multiplied by 2. Now, when we talk about how loud a sound wave is, this is associated with the energy or the amplitude of the sound wave. Louder sounds have more energy. The loudness of a sound is measured with intensity. It's measured in decibels or dB. The decibel scale is logarithmic, which means that an increase of 10 decibels in intensity level means the sound is perceived to be about 10 times louder. Above about 100 decibels, sound can begin to cause physical damage to the inner ear and can cause some temporary or permanent hearing loss. If we look at the intensity levels of various sounds, and they have pain and extreme pain at about 125. I've heard it to be at about 100. 100 decibels is what you might get at a concert if you're pretty close to the amplifiers. This is why so many musicians have hearing loss. They spend all those hours in front of the amplifiers, and the loudest rock bands are about 100 decibels, and that can do some damage. 140 would probably be enough to make you bleed from the ears. So they have extreme pain. I think that's on the conservative side. Now everybody has at one time or another sat for a hearing test. Whoever gives you the test is trying to reproduce this curve that you see here. This is called the threshold of hearing, and what it shows is the intensity level that a particular sound needs to have in order for you to hear it. Across the bottom of this graph, you see the range of human hearing ranges from 20 hertz down here up to about 20,000 hertz. Most people have a curve like this. What we see is that for a given frequency, there's a particular intensity level that the sound needs to have in order for you to hear it. For example, if we look at 100 hertz and we go up to the graph, it's just above 30 decibels. That's how loud it needs to be in order for you to hear it. Of course, this varies by frequency. What you see here, this range of frequencies is what you can hear best. So obviously it needs the lowest amount of intensity level in order for you to be able to hear it. These sounds are associated with S's or SH, sh. Those sounds resonate in your ear canal. We'll be talking about resonance a little later. Most mammals have ear canals that are about the same size, and they tend to hear best at these frequencies, right around 3,000–4,000 hertz. Even if the range is different, dog whistles are at about 40,000 hertz. Dogs can hear them, but you can't. Bats use echolocation; they squeak at about 100,000 hertz. But at any rate, the range of sounds that mammals hear best is right about in here. This is sometimes thought of as an alarm frequency, which is why a rattlesnake rattle is in that region also. Now, when we talk about how the ear actually works, we have the ear flap or the pinna, which is out here. Here's your ear canal. At the back end of your ear canal is the eardrum. And the waves that we saw before, the alternate areas of compression and rarefaction, enter the ear canal. When the high pressure area hits the eardrum, it pushes the eardrum in. When the rarefacted air, which is at low pressure, hits the eardrum, it pulls the eardrum out. And the eardrum effectively vibrates with the same frequency as the sound. Now, when the eardrum vibrates, there are three little bones here. You can see the hammer, the anvil, and the stirrup. They're also called the ossicular chain, and they are three bones that transmit the vibration from the ear canal to, there's an organ in here called the oval window. You can't see it on the diagram, but it's at one end of this snail shell looking thing called the cochlea. The cochlea is where the sounds are actually perceived. The cochlea is a tube that's kind of rolled up. It's got fluid in it. The waves from the vibration of the eardrum get transmitted through the ossicular chain, through the oval window. They send waves through the fluid in the cochlea, and that makes there's little hairs in the cochlea, and they vibrate back and forth. And that sends a message through the auditory nerve to the brain that you've actually heard something. There's some other interesting things about the inner ear. These are your semicircular canals. These are the organs of balance. There's one in each plane. It's tough to see in a two-dimensional diagram, but this is what tells you which way your head is oriented, even if your eyes are closed. They're sometimes called the organs of balance or something to that effect. When you tilt your head to the side, the fluid in the semicircular canals moves, and again it tells your brain which way is down, effectively, which way gravity points. All right, so that's sound and hearing. Next up, we'll talk about resonance and the Doppler effect. Until then, enjoy. I'll see you again soon.